All right. Good morning, everybody. Hope you're all doing well. How did the quiz go?
Good morning. It went pretty well, I think.
Okay, yeah, that's good. So I think this was a Gauss's law problem. Is that correct? So that type of problem, right, is one that would be a pretty common kind of question and is something that you should definitely feel confident doing. So I will also be working on, so I guess going back to the announcements, right, today, this week, we are going to work on electrostatics today and also on Thursday, right? So this is the last week of new material. And then next week, we'll have 1 day of review. And then you'll also take the exam at the testing center. So over the weekend, maybe by Thursday, I'm going to put up a few more questions, like just a few more random practice questions that you can do. They won't be due or anything, but stuff that you could review on your own. And some of those will also be Gauss's law problems, since those are pretty common and good ones to understand. So I'll be posting those definitely before next Tuesday and possibly before this Thursday, in order to give you some more things to look at before the exam. And then the exam is still on Thursday, September 30th. So that's in a week and 2 days. Yeah. Okay. Any questions about the exam, the class, the homework, etc.? All right. Okay, so let's start doing some homework 4. All right. So let's move on to this problem of the problem 3. It's like this circular disc. Let me put this on our notes today. Where did you all go? All right. And before we do that, let's take a look at the Moodle page. All right. So I know, so last week I mentioned that I had put these two things up here. So these go back a little bit, but homework 3 and homework 4 are just, they're inevitably very interconnected, right? Because they're all about the electrostatics. And then homework 3, we looked a lot more at finding the electric field, right? So we found the electric field, and we used 2 methods. We used Coulomb's law, and we also used Gauss's law, which were really just kind of variations on each other, right? And in the process of doing that, we looked at a couple of these problems, and these are in the book, right? So if you look in the textbook, in the Ullaby electromagnetics, you can find these 2 examples. Actually, if you can pull that up now, possibly. And these 2 examples, these are very classic problems in electrical engineering. One is the ring of charge, right? And so this one is sometimes called an annular charged ring or circular charged ring, something like this, where you find the electric field on the z-axis. And then this problem, which I uploaded a solution for yesterday, is the annular disk. And this problem is very similar to the annular ring. But instead of being a ring of charge, it's a full disk of charge, but you're still trying to find the electric field at this point. So in your textbook, do more of you have this version or this version? 7th or 8th?
I think I have the 7th.
Okay, they're basically the same, but I'll pop open the 7th and show you where we're at and what I'm talking about. And there's solutions in your textbook for how to find all right. I do not have access right now. Let's see if we have access to the other one. So they both, yeah, okay, great. These both give ways of finding the electric field. They rely a little bit heavily on using the geometry, and that's okay, but I wanted to upload some solutions that show how to use the cookbook, which is a highly vector-based method. Okay, and so this, okay, yeah, here we are. So this, if you look in your textbook, you have this example 4.4 that shows you how to find the field of a ring of charge. And again, this is a very classic problem, right? If you look in, right, here's an old book called Electromagnetic Waves and Radiating Systems from Jordan and Balmain. This book's kind of famous. This one has that problem in it. This is another classic book, Height and Buck. This also has the same problem. I have other textbooks. This problem is something that is always shown, and I just wanted you to be able to see the solution using our methods. And we're going to use it today because in the chapter 3, we focused on the electric field. And in chapter 4, we're looking a little bit more at electric potential. But as we saw last week when we started this, right, they're related, right? The electric potential and the electric field are related, right? And they're related by the gradient, right? So that taking the gradient of that scalar field, the voltage will give you the electric field, which is a vector. And so so in this textbook, you have these two. I also redid them using more math and using our cookbook method. They arrive at the same result. So there's this result, and then this is the electric field of a circular disk of charge. And they arrive at this result, which I have done in here, and it's all the way at the bottom. I included, more steps than is probably necessary, but they are available so that you can study how to use the cookbook method and also how to arrive at some of these very classic solutions. The reason I included a longer version as well, so I know I mentioned this on the ring one, and hopefully you did take a look at it. So in the ring, it's easy to start out using the cylindrical coordinates, but there is a little bit of a hang up, which is that if you use the cylindrical coordinates, when you try to integrate this vector, this radial vector will be pointed in many different directions, and so the result won't make sense. And so it's better to convert to Cartesian. So in the version that I uploaded, again, you will arrive at the same result as shown here in the textbook. But the work that I've shown shows you how to do this start to finish using pure vectors, using the cookbook method, and including this conversion from cylindrical coordinates to Cartesian coordinates. So there's a lot of different things that you could practice by looking at this method that's in the cookbook. And again, the result will be the same as what you see in the textbook. In the annular disk solution, it's very similar to the annular ring. And so if you go ahead and look at this later, you can see that everywhere that's red, this is just the only things that changed from the ring to the disk. Okay. All right, so why did I just spend all this time telling you about electric fields again? And that is because this other homework problem we have, right? It says that you have a circular disk of charge, and now we want to obtain an expression for the electric potential. Okay. So before we started with the disk and found the electric field, now let's go the other way and look at this problem and find the electric potential. Okay, now if you look in the textbook, there is some equations for how to find the electric potential. Okay. And this will be a little bit more lecture based because I'm not sure how much is in the videos, but I feel like in the past I had not covered electric potential very well, and I want to cover electric potential a bit better in this class. And so we have this expression for the voltage, 1/4 pi epsilon. Oh, sorry. Can you not see? Are you seeing this?
Yeah, we can see it.
Okay. So if you go in the textbook, you'll find this expression, rho s r, call this RSP ds. Okay, now this is, there is a set of these equations. I'll go back to the textbook here that I'm pulling these from. Okay. So this set of equations in the textbook is describing distributions of charge. Why can't I find it? Here they are. So any distribution of charge, volume, surface, or line distributions of charge, a way to find the voltage due to them. Okay. So this is what the textbook says. So if we want to go, if we have a circular disk with a radius and we want to find a uniform, and it has a uniform charge density across the surface, and we want to find the electric potential, we have this information about volume, surface, and line distribution. So the first question we should ask ourselves is, if we want to find this electric potential for this disk, what kind of charge distribution is this? Is it a volume, a surface, or a line?
Surface.
Yeah, it's a surface, right? This is a very thin, right? It's a very thin. And then also we're given, right, that this is a rho s. So all these things, right, should point to telling us that we have a surface distribution.
Did you forget to switch your screen?
Ah, yes, I did. Thank you. Thank you very much. All right. So, so we have a surface distribution. Right, so we've selected a surface distribution. We know that this is a thin ring of charge. And so now, if we want to use the equations, right, there's a couple things we should figure out. One, right, we know this is not changing, but we should figure out what our ds is going to be. And we should also figure out what this r prime is going to be. Okay, so let's start with the ds, and what the textbook says and what we should know is that we're getting a scalar. So this should be a scalar. Okay. And the ds is going to tell us what is changing on the surface. So if we move around on this surface, what changes? We have r, phi, and z's. Which things are changing on this surface?
R and, wait, no, is it just B or is it R and?
So there should be two, right? Because this is a surface. We know that this is going to be a surface one. So if I move around in this red, if I move around anywhere on the red, is R changing?
Yeah, R is changing.
Yeah, so we're definitely gonna have an R, and then if we move around in the red, is phi changing?
Yes.
Yep, and phi is also changing. Okay, and then, right, because this is cylindrical coordinates, right, we should say, I don't know if I have my cookbook open, but you should open your cookbook, right, and you should say, this is cylindrical coordinates. There's probably something special about the DS, and we should double check on that. And yes, right. Okay, if we look at that, right, we are dealing with a scalar DS, but we have dr, d phi, so we should have our ds be equal to r dr d phi, right? And so this is the scalar version. Okay, so we found ds. Now what about this r? Okay. And in the textbook, pop back over to it. The textbook says that the r is defined as, I'll just pull all of this. The r is defined as the distance, right? This r prime is a magnitude between the integration point and the observation point. So it's the magnitude between the integration point and the observation point. And so this is something we've done in our, similar to what we've done in the electric field. Where the integration point, this is the source, charge source. And the observation point, this is the point that you're interested in. Okay. And so we could write this as RP minus RS, right? Does this make sense to you? So the integration point, this is the integration point. And this one is the observation point. So on your piece of paper, see if you can find this vector. Okay, so right, we have integration points, right? These are on this disk, and then we have an observation point somewhere up here. So on your paper, see if you can write this vector of this vector magnitude, r prime, where we have rp minus rs, where we have the magnitude of that vector. So if you want to break this down and make it easier, first write rp, then write rs, and then write rp minus rs, and then find the magnitude. All right, so what is a vector from the origin to the observation point? Let's see. What do you think, Daniel?
I have no idea.
All right, so if it's in cylindrical, what is a vector from this is the observation point, right? So what would a vector from the origin to the observation point be? What, does it go anywhere in the r direction?
Oh, that's gonna be H because it's only moving in the Z direction.
Yeah, so we could write 0. So you're saying 0, 0H, is that correct?
Yes.
Okay. Someone else, what about from the origin to the integration point, the point where the charge is? What should this be? Let's see here. AK, what do you think?
I'm not sure. What is it going to be?
All right, so if I go from the origin to any point on this disk, will it have an R magnitude?
Would it will have an unknown, we can use a variable for that, right?
Yep.
For both R and phi.
Yeah, so R, and this is a little tricky since we chose 0 for phi, we'll also choose 0 here. But really it's irrelevant, right? Because any from this point, because we're trying to draw ultimately what this is, this is the magnitude from a source point to a integration point, right? So this is really, let's say it's this point. It's really this magnitude. It's the length from the observation point to the source point. And so they will always have the same phi. Does that make sense? So there's a little bit of a weird thing, right? Where on this axis, what is the value of phi when you're on this Z axis? What do you think it is? It's kind of a trick question. When you're on this axis, what is the value of phi?
It's both 0 and 2 pi, basically.
And everything in between. So no matter where you are on this axis, right, it's inclusive of all phi values. So it's a little bit of a weird trick, right? So from here, from this point up to here, also, right, the phi value on the axis at the point will match the phi value of this integration point. The phi value at this point matches the phi value here. And that's because when you're on this Z axis, right, this is like a pole or a post. And no matter if you look around, right, you can stay in the same point and spin 360 degrees, 0 to 2 pi, and it will be inclusive of every angle without actually moving where you are on that point. So this is a little bit a trick question, but basically since we chose 0 for this RP, we should choose 0 for this RS. Alternatively, you could say it's a variable and say it's phi, this is phi, and this is phi. Ultimately, it will just go away. But so I think Daniel said the R should be a variable, right? Because if we're going from this origin out to here, out to this source or to this source, right? It's a variable R, it changes, right? It changes depending on where you are on the disk. And what about Z on this disk?
Should be 0.
Yeah. Okay, so now what is this vector?
Zero.
RP minus RS. All right, let's look at the first one. So what is,
Sorry, I was multiplying it.
okay. No worries. So in this direction, right, we should have minus R, and in the Z direction, have this. Okay, and so what's the magnitude of this?
It'll just be the square root of r squared plus z squared.
H
Yep.
squared. Or Z
Yeah.
squared.
And we already chose a specific H. But we could have chosen, yes, okay. To obtain an expression for a point anywhere on the Z-axis, we could have substituted this, made this a variable Z. And oops, yeah. So we could write this for any Z. This is the most general case. For any Z, this is what the distance is, right? And so what we just did, right? All we did, right? This is just, we just did the Pythagorean theorem basically, right? We just made a triangle and we figured out what our variables were going to be, right? We have this some triangle between, right, our observation point out here, which has some variable R, and then some height Z that we are observing at. And we just figured out, right, what this length is. That's what we just did. We just figured out the length. And the reason, right, we wanted to do that is, remember the voltage potential, right? It matters. You have to figure out some path from your observation point to your charge point. And the voltage potential is a scalar potential telling you how much that voltage changes from where the one point to another point. So that's why we need to have some path between these two things. Okay. So now we have got basically everything we need, right, in order to finish this up, right? We just figured out what this R prime was, and we figured out what DS was to start with. So let's put it all together. And we said DS is R dr d phi. Okay, so if we want to do this integration, what should our limits be? So try to set this up, see if you can figure out what the limits should be. Right, so we have this, the disk has a total radius of A. So see if you can find limits and solve this integral, okay? Okay, anyone have the limits for phi? What should those be?
Let's go to 0 to 2 pi,
Yeah, and what about r?
0 to a.
Yep, perfect. All right, so if you haven't got this far, these are the limits. Now, I would recommend if you haven't or you're getting stuck on this integral, maybe try an integral solver or your calculator.
So do we need to practice revise our integrals for the exam, or should we?
If the integral, so if the integral is really hard on the exam, the problem will either end at a place where all you are supposed to do is set up the integral, or I would give you maybe a set of integrals or an integral table that might give you some options so that you can see what the answer is for, or what some potential answers are for a difficult integral. Because if you've noticed, right, almost all of these have ended up with a pretty similar format, right? Like something either like r over r squared plus z squared raised to the 1/2, or r squared plus z squared to the 3/2, or 1 over r squared plus z squared to the 1/2. They're all, a lot of them are pretty similar. So that you'll either, the solution will either be to set the integral up or to use an integral table. Yeah. All right, did anyone get an answer?
Yeah, I did. I got 1/2E, the rho s, I think. I think that's what it is, yeah.
Yeah, row
And
S.
then, and then in parentheses, the square root of z squared plus a squared, then minus z. That.
I believe this is what I have also. Here, I'll make it a little bit easier to see also. Like this, basically. Okay, anyone else get this? This should be correct. This is what I got also. All right, so now you have an expression for the voltage, right? And that is part A. Okay, so this is the answer for A. Now for B, right, we have this relationship between the electric field and the voltage. So you can take your expression here and you can solve this. And this, right, you should be able to do this one somewhat easily because, right, when you are working on this, right, you're taking the gradient of the voltage, right, and our voltage, our expression for voltage looks like this. So is our expression in voltage, does it have any x? What's the partial derivative of this with respect to x?
0.
Yeah, so that one's 0. What about with respect to y?
0.
Yeah, that one's 0. So you really are just going to have this. Okay. And then in part C, all you're doing is just taking the expression, right? So you're going to get an expression for the electric field, and you are just going to evaluate it at Z equals H. Okay, and then in D, compare your result. Do you think it should be the same? Yes or no? Give me a thumbs up if you think yes, it'll be the same. Thumbs no, thumbs down, no, you don't think it'll be the same. All right, I think Calvin's the only person, he was not sure. So Daniel, what do you think? Going to be the same or not the same? You might be muted. Still not hearing you, but that's okay.
Oh, sorry. I thought I was already unmuted.
Um,
I think it would probably not be the same.
Okay. Anyone else? AK, what do you think? Same, not the same? Why? Why not?
I'm going half and half, to be honest.
Yeah, what makes you not sure? What's holding you back from one way or the other?
I don't know. I think because of the way I solved it, I got somewhat similar, but not quite the same. So
Yeah.
that's why I wasn't sure, but
Okay.
I would say it's almost close to that, like
Yeah.
similarity. So
Yeah, it should be very similar. And you can also compare your result. You should compare your result you should compare it to this. Okay. And, oops, come on. Sorry. And you should also compare your result, okay, to the one that I put up on the Moodle page, okay, which was this one. All right. Right, and this is also slightly different. Okay, so you should compare your result. You can compare it to both of these. And in fact, I believe this, yeah, there may even be a small issue. I don't know if it was from me copying and pasting or from the book, but my hint is that one of the reasons is this should be plus or minus a plus or minus z. And so they've done a little bit of a tricky transform to this absolute value of h. And so they have this plus or minus. But compare your result to these. All right. So this problem, right? This problem in the end, what I want you to see is that you could use methods that we understand to solve for this scalar value, the voltage. So we could start with our surface and charge distribution. We could solve for that scalar voltage first, and then we could apply the gradient in order to get the electric field, or we could start with the electric field and we could find the voltage. All right, and so these values are very related to each other, right? The electric field describes a vector field and the voltage field describes a scalar field. And that scalar field of the voltage is really just telling you how much the electric vector field is changing. Okay, so that the voltage is a description of how much your electric field is changing. And so whenever you're using your voltmeter, right, making a circuit, right, there's alternative ways of thinking about this, right? You could think of it in terms of all these field theories that the difference in voltage is simply just a difference in electric field strength, different parts. So that's kind of the point of this problem. And also it's to take another look at this, classic problem, which is what so much of this early electromagnetics is looking at these classic problems. Okay. The later section, when we do transmission lines, we will look at more applied problems. But for now, we're just looking at a lot of these classic problems. Okay. Let's take a look at this problem 4 and set this up before we end today. So problem 4 asks to determine the electric potential or voltage at the origin due to 4 20 microcoulomb charges residing in free space at the corners of a 2 meter by 2 meter square that's centered about the origin. Okay, on the XY plane. So we're in the XY plane. On your paper, draw the location of each of these charges. Okay, so make a diagram of this. Make a diagram of what is happening in this problem so that we can use it for the final solution. So step 1 is to make a diagram here. And if you have it drawn, take a picture and upload it. All right. Did anyone else get this?
Yeah, I got that.
Okay, perfect. All right, so the square.
So my question is, so I did that, but
Mhm.
then when they, in the question, they included the 3 coordinate points. So should it not be in a 3 coordinate system? So I did it in both, but in that.
Okay,
in
so
the-
yeah, so I think this, let's just annotate this a little bit then. So this would be 1. This would be 1. This would be -1. This would be -1. So this point is at 1, 1. Is it in? Yeah. So charge 1. Is this making sense? Then charge,
Yeah.
okay. And then charge 2 is at 1, -1, 0. So this one, oops. Okay. Okay. Now, right, there is, if in the textbook, right, we can, similar to what we did with our distribution, right, we have some information about voltage where Q is equal to 4 pi epsilon. Q due to voltage due to 1 charge is equal to 4 pi epsilon. And then it says RS, or sorry, so in the textbook, I believe it says R minus R1. Okay, and so for us, right, we know that this is the same as 4 pi epsilon, and it is the RP, right? So the observation point minus the source point, right? So this is a magnitude, this is some scalar that we're trying to find. So in order to get this voltage, right, we can write RP, right? And this is a vector from the origin to the point that we're interested in. And what would that be in this case? So the observation point, I think, was at the center, right? That's,
Right, it's the origin.
yeah. So what is this vector RP? What's the vector from the origin to our observation point?
It's just zeros.
Yep, yeah, right, this is our point, right? Point P is 0, 0. So it's 0 plus 0 plus 0. And if we're doing this for charge 1, say voltage 1, what is a vector from the origin to the source point?
1, 0.
Yeah, 1, 1, 0. Okay, so then what does this magnitude equal?
One.
Yeah, so RP minus RS. This is, well, first RP minus RS is minus X hat. Oops. Is this what you got? Does this make sense? Okay, so now, and we know this Q, right? We have the 4 charges are each equal to 20 coulombs. 20 micro coulombs, pardon me. So the voltage due to the charge 1, right, is 20 micro coulombs over 4 pi epsilon root of 2. Now you might realize, and we're about out of time, you might realize though that, right, we made a vector from here to here, and then we found the magnitude, right? So the magnitude of this was root 2. And we have 4 charges, right? We have 4 charges we need to figure out. And what do you think the distance or the magnitude of the vectors for each one of these is going to be?
Exact same.
Exact same, right? They're each going to be root 2. Now, do you remember superposition, right? And that worked for electric fields, right? Superposition works for electric fields. And, right, we had this relationship, oops, but for superposition on electric fields, and electric fields are equal to this. And do you think that superposition should work for derivatives also? Can we sum up derivatives? Could we find V1 plus V2 plus V3? The answer is yes. So voltage also follows superposition. So voltage also follows superposition. So we just figured out how to solve for voltage 1, right? Oops. And the total voltage will be V1. It'll be the voltage due to each different charge. Okay. All right. Sorry, I took you a couple extra minutes. But the voltage, right, this also follows superposition. Hopefully you are starting to have a better feel of how charge, electric fields, and voltage all relate. On Thursday, we will look at a couple other things, boundary conditions, and a couple other things about charge, but we'll kind of wrap everything up. So if you have any questions, stick around. I'll be here for a few more minutes. If not, take off. Have a nice day, and I'll see you later. See ya.